deductive arguments with chains of conditionals. This is if we have more than one conditional statement attached together to form some sort of conclusion. All right, so let's start with the premise. If P then Q, and we'll add a secondary premise. If Q then R, so our conclusion, this is why they call this a chain of conditionals, is if I know P happened, then I can jump straight to say that R happened. If I know P, then I know R. So P implies R simply because of this chain connecting property. Okay, determine the validity of this argument. If elected to the school board, Maria Lopez will force the school district to raise academic standards, which will benefit my children's education. Therefore, my children will benefit if Maria Lopez is elected. Oh my, we get a lot of statements here. All right, so let's first go through the premise. So our first premise is if elected, then, well then what? We'll raise standards. Okay, so then the other premise. So in the next sentence, if then standards are raised, then, well then what? Then my children will benefit. So then children will benefit. Okay, so conclusion. Conclusion would be if Maria is elected, then what, based on this chain of conditionals, then the children will benefit. Okay. Now, because of this idea of a chain of conditionals, that's actually a valid argument. It may or may not be true, but it is a valid argument. That if we understand that if we accept those two initial premises as true, then the conclusion based off those premises also have to be true. Okay. And typically in math, we rely on this idea of proofs and theorems. So a mathematical proof fits under the umbrella of a deductive argument. It's a series of connected statements that imply the truth of a certain claim. Let's see. And this claim is what we call a theorem. So it's a larger statement that we've used a proof to show. Let's see, so statement defined by a proof. Okay. If the argument is considered to be valid and sound, then the theorem is considered to be proven. So if it's valid and sound, so if it fits all the other criteria that we talked about earlier, then we say that it's a proved statement is proved. Okay. All right, so we're going to look at a statement A times B equals B times A. So we're going to we're going to test this and sort of remind ourselves what we're doing here. So let's say I pick small numbers like a equals 1 and b equals 2. Is 2 times 1 the same as 1 times 2? Well, that's true. What about a equals 10 and b equals 5? Is 10 times 5 equal to 5 times 10? Okay, that's, again, true. Let's have some fun with this. Let's put some fractions in here. What? So let's say a is a half and b is 3/4. If I'd have 1/2 times 3/4 and 3/4 times 1/2, do I get the same answer? Well, 1 times 3 is 3, 2 times 4 is 8, so I get 3/8 both cases. So at this particular moment, we would say that, yeah, this looks like it's true, but is this proved? Have we given a deductive argument that that's actually true? And the answer is no. It's actually an inductive argument that we picked. And so all the numbers, all the examples we came up with were specific. Now, we've seen numbers enough that we think it's a true statement, but we would have to come up with a very generalized deductive argument, and that's what makes math professors, is the fact that they go and study and learn how this stuff all works. So anyways.